Welcome to your 7.6 video on solving exponential and logarithmic functions. Throughout the course of this book, as well as throughout the course of our school year, I hope you've noticed that every time we get towards the end of the chapter, the last thing the book does is take the skill and take the strategy that we've learned in that chapter and apply it to actually solving a function or solving an equation with those skills involved. And so chapter 7 is no different. We're going to take exponentials and logs and try and throw them into an equation and try and figure out how to solve for a variable within a function when those exponentials and logs are within them. So there's really two rules for the day that I want you to abide by. Rule number one. The rule number one says if b to the x equals b to the y, then x has to equal y. In other words, if I have two exponentials, b to the x and in the other exponential, b to the y, if the bases are the same, notice that the b and b are the same, then it must be true that the exponents in those exponentials must also be the same. In this case, x must equal y. So for example, on the bottom of the screen it says, hey, if 3 to the x is equal to 3 to the fifth, if the bases are the same at 3, then it must mean that x has to equal 5. Pretty simple. Now let's go ahead and try and apply it. Notice at the very top of the screen, it says check for extraneous solutions. We learned that last chapter. Extraneous solutions are solutions that are created during our solving process that may not all actually work when we plug it back in the original. So be careful with that. That implies that we're going to have to check things along the way. So look at number one. I have 4 to the x equals 4 to the 3x plus 2. Okay, a pretty easy one because immediately you see that I have two bases that are exactly the same, 4 and 4. If that's true, the rule number one says if the bases are the same, then the exponents also must be the same. So x must equal 3x plus 2. Here's the x, and here's the 3x plus 2. Then simply go ahead and solve. Minus 3x to both sides. If I do that, I think I get negative 2x is equal to 2. Divide by negative 2 on both sides, and I get x is equal to negative 1. Now, I still got to check, so let's go ahead and plug it in. That's implying to me that if I rewrite it over here, that really means I have 4 to the negative 1 should equal 4 to the 3 times negative 1 plus 2. Well, that means 4 to the negative 1 should equal 4. 3 times negative 1 is negative 3, plus 2 back is negative 1. Sure enough, it works. Okay, that is definitely a solution to that function. Look at number 2. I have 3 to the x equals 1/9 to the x plus 3. Immediately you see the bases are not the same. So it's going to be your responsibility to go ahead and try and figure out how can I get the bases to be the same. So I might take 1/9 off to the side and say, hey, can I get 1/9 to look like something, or 3 to the something? Well, would you agree that 1/9 is really 1 over 3 squared? Really 9 is 3 squared, it's just in the bottom this time, so 1 over 3 squared. And what if I said I want to put 3 on the top? Well, if I put 3 on the top, 1 over 3 squared should be exactly the same as 3 to the negative 2. And so if I have that, I immediately turned 1/9 into a power of 3. And so if I look at that and I bring it back to my problem, I have 3 to the x equals, I'm no longer going to put 1/9. Instead, I got 3 to the negative 2, still all raised to the x plus 3. Now, because I did that, you can see now that my bases are the same. Now I just got to simplify a few things, especially on the right side. On the right side, I have a power to a power, so I know I need to multiply those. And so if that's the case, I have 3 to the x equals, and I still have 3 to the negative 2 times x plus 3. Remember to give the negative 2 to both the x and the 3 because you're multiplying the entire quantity. And when I do that, I should get negative 2x minus 6. And if that's the case, I now have a base equaling a base. And so if that is the case, I can go ahead and say the exponents are the same. So x is equal to negative 2x minus 6. That means if I add 2x to both sides, add 2x to both sides, I get 3x is equal to negative 6. And I'm going to go ahead and change markers here so we can see it. Then I'm going to divide by 3 on both sides, so I think I get x is equal to negative 2. Again, let's check it. Okay, if I were to check this over here, so I'll just kind of draw a line. Okay, if I were to check this right here, I think I should get 3 to the negative 2. I'm using the original function, just putting in x. So 3 to the x turns into 3 to the negative 2. And I'm going to keep 1/9 as 3 to the negative 2 because it's a lot easier to see if I can do that. So it's 3 to the negative 2 to the, it was x plus 3. I know x to be negative 2 plus 3. So I'll simplify. I have 3 to the negative 2 equals, if I go ahead and do this, this is really 3 to the negative 2. Negative 2 plus 3 is a positive 1. And when I have negative 2 times 1, I think I get 3 to the negative 2 is equal to 3 to the negative 2. Sure enough, it works. What about number 3? It says 9 to the 2x equals 27 to the x minus 1. Same issue. I don't have the same basis. Okay, but I already know something's up because I can see that 9 and 27 are multiples of 3. So would you agree that if I had 9, that's really the same as 3 squared, still all raised to the 2x, equals 27? Well, 27 is really just plain old 3 to the third, all raised to the x minus 1. And now, just like the last slide, okay, I'm going to go ahead and reduce those or simplify those exponents. 3 squared to the 2x, well, that's squared and 2x, you're going to multiply because it's power to a power, so I really have 3 to the 4x is equal to 3 to the 3 times x minus 1. Just like the last one, you're taking 3 and multiplying it by the entire quantity, x minus 1. So I think I get 3x minus 3. And so if that's the case, again, I can see that I have a 3 and a 3. That must mean that 4x is equal to 3x minus 3, the two exponents. And then I'm going to go ahead and subtract minus 3x from both sides, or subtract 3x from both sides. 4x minus 3x is x, and I just have a negative 3. So I think my answer is x equals negative 3. Now, again, let's plug it in. I'm going to just do it over here and check it over here, and then I'll erase it so I can do number 4. If I look at it, I had 9 to the 2x. Well, I know 9 was really 3 squared to the 2x, which is really 2 times x, which is now negative 3, equals 27 was 3 cubed to the x minus 1. I know x to be negative 3 minus 1. Start simplifying. I really have 3 squared. 2 to the negative 3 is negative 6 equals still 3 to the third. But then negative 3 minus 1 more is negative 4. And you can kind of see where this is going, because if I look at the left side, I really have 2 times negative 6 is negative 12, and 3 times negative 4 is negative 12 as well. Sure enough, it works. Okay? Go ahead and pause the video and try and do number 4 on your own. I'll give you a few seconds here, and then I'll go ahead and move on, and I will help you fill this in tomorrow in class. So try and do number 4, 81 to the 3 minus x equals 1/3 all raised to 5x minus 6. Now, what happens when the base is not the same on both sides of the equation? Now, I'm not talking about the ones we just did, where we can manipulate the sides and we can go ahead and try and manipulate to make them look the same. What if it physically isn't possible? Okay, I want you to remember one thing. We've talked about this. The one thing I want you to remember is the fact that log base b of b to the x is equal to x. In other words, we talked about in class, if I have a log with a base b right next to an exponential with the same base b, or vice versa, if I have an exponential with base b and I raise it to the same log base b, okay, I know I'm just going to get that x back. Okay, and so if that's the case, that's going to help me go ahead and solve a few things. Okay, in other words, if you have a base b in both the log and the exponent, so they're both the same bases, and the functions are immediately next to each other, I know the log and the exponential is going to cancel out, and you're just left with the x value that's remaining. Okay, so let's go ahead and take a look at this. Notice again, I want to check for extraneous solutions. I don't want to screw this up. Okay, and so when I look at this, in number 1, I immediately see that I have a log base 4 right next to an exponential for the x. I'm doing log base 4 of the exponential 4 of x, or 4 to the x. And so when I look at this, I immediately say, hey, I know something there. That's going to cancel out. That doesn't work anymore. So if that's the case, I get x equals 5. Okay, if you look at number 2, okay, if I look at number 2, it's the same thing, but now I'm going a different way. Instead of having a log, now I'm taking a power, I'm taking a base of 5 and raising it to the log base 5. Again, I have a big base paired with the log with the same base 5, and if that's the case, that's going to cancel out, and I get x equals 10. Of course, should be taking the time and re-plugging that back in to make sure, including the change of base formulas to actually go ahead and do that. But for right now, be confident in the fact that these are going to work. In number 3, I have 9 to the x is equal to 35. 9 to the x is equal to 35. Now, we could go ahead and do this whole process and change in the logs, and I could say, okay, I could change this into a log function because I want to get the x out of the power. So I could say, okay, log and equals, my base is 9, so I'm going to raise 9 to the x, and I'm going to go ahead and get out 35. That's what the problem is telling me. And then I can go ahead and take the log base 9 of 35, use a change of base formula, and go ahead and solve it that way. I think that takes way, way too long. Okay, and so why not instead? Okay, why not instead do this? You know I want to get x out of the exponent. In order for me to get the x out of the exponent, I need to get rid of that base 9. If I want to get rid of that base 9, I know from previous slides, what if I throw a log in front of it? Okay, so in other words, what if I say, hey, I want to take the log base 9 of the entire left side. And if I do it to the left, this to be fair, I also got to do a log base 9 of 35 on the right. Keep a balanced equation. Well, I know if I take log base 9 of 9 to the something, I know what's going to happen with these. All those things right there are immediately going to go away, and all I have left is simply x on the left side equals exactly what we came up with before, log base 9 of 35. Okay, now all of a sudden, I can go ahead and solve it. If I have x equals log base 9 of 35, I think I can actually calculate that. Because now, I can go ahead and say, well, I can do that in my calculator. That really means I have the log base 10 of 35 divided by the log base 10 of 9. Change of base formula. So if you type that into your calculator, I have log of 35 divided by the log of 9. I think I get an x value of 1.618. There's my answer. Okay, let's look at number 4. Okay, when you look at this, again, I want to get that 9x, or I want to get that x out of the power. That means I need to get rid of the 7. If I want to get rid of that power of 7, I'm going to take this entire side and do the log base 7 of it, because I know it's going to cancel out. It's really an opposite operation. Okay, so if I do it to the left, I really need to do it to the right. Therefore, the 7s are going to cancel out. All I have left is simply the power, so 9x equals log base 7 of 15. And if I want to go ahead and get x by itself, I'm going to divide by 9 on both sides. And when I do that, I get x is equal to this whole mess. But we can go ahead and figure this out because really this is log of 15 divided by the log of 7. And once you get that answer, then we're going to divide it by 9. So go ahead and take out your calculator. I'm going to do log of 15 divided by the log of 7. When I get that, I'll get rid of this x momentarily. Okay, when I get that, I think I get something along the lines of 1.39 all divided by 9. And I'm going to divide that previous answer by 9. And so I think I get x equals 0.155 if I round to the nearest decimal. All right. Rule number 2. Rule number 2 is exactly the same as rule number 1, but where rule number 1 used exponentials, rule number 2 uses logs. Rule number 1 said if I have two exponentials equal to each other with the same base, then the exponents need to be the same. The same thing goes for logs. If I have two logs with the same base, then I know what you're taking the log of are also going to be the same. So you can see here in this problem, okay, or in the if part in rule number 2, it says if I have a log base b of x, and it's going to equal a log base b of y, then I know that those two items I'm taking the log of must be exactly the same. So again, for example, if I have a log base 3 of x, notice that the log bases are the same, and it's equal to log base 3 of 5, I know what you're taking the log of. In this case, x and 5 must be identical. This is the same strategy, but instead of being in exponential form, we are now in logarithmic form. So again, let's start out easy here and kind of work our way towards something a little bit harder. Okay, so when you look at this, I have log base 4 in number 1. I have log base 4 of x equals log base 4 of 6. I see I have log 4 and log 4. So if I have the same base logs, that I know they're going to be exactly the same, so I know x has to be equal to 6. If you look at number 2, again I see log base 4 equals log base 4. If that's the case, I know what you're taking the log of need to be exactly the same. So if that's the case, I know that 2x plus 8 has to equal 6x minus 12. And now go ahead and solve minus 2x from both sides. So I get 8 is equal to 4x minus 12. Add 12 to the other side, so I get 20 is equal to 4x, and I think I get x equals 5. Again, make sure that you're plugging it back in and you're checking for extraneous solutions. I'm putting it at the very top there just so we are aware of it, but for the term and for the sake of the length of this video, I'm not going to check. But please, please, please go back and check and make sure you're getting answers that actually work. Okay, if you look at number 3, okay, I have log base 7 of 3x minus 2 is equal to 2. Now, I no longer have the situation where I have two logs equaling each other. Instead, now I got to say, okay, I want to get inside of that log. I want to get inside of that log. I want to get rid of the log so I can get x by itself. Well, in order for me to get rid of the log, okay, it goes back to knowing, okay, that if I go ahead and put log base 7 next to something that has a base of 7 for an exponential, I know I get to cancel out. So why wouldn't I do this? Why won't I say, hey, I'm going to raise the entire left side, okay, and have a base power of 7. So I'm going to take 7 to the entire left side. So now the entire left side becomes the exponent. If I do it to the left, I also must do it to the right, because now I have 7 squared on the right. Okay, the reason why I do that is because now if I take 7 and I raise it to the log base 7, I have two things, two items, an exponential and a log, that have the same base. If they have the same base, we know by rule they're going to cancel out. If that's the case, I now have 3x minus 2 equals 7 squared, or really 49. And now it becomes a simple algebra problem. Add 2 to both sides, and so I have 3x is equal to 51. And divide by 3 on both sides. And when you divide by 3 on both sides, you should get 17. So x has to be 17. Again, checking your work is vital here. Try to number 4. Number 4, hey, I want to get rid of the log base 4. Because if I get rid of the log base 4, I know I'm going to get inside and be able to solve for x. How do I get rid of the log base 4? Well, let's go ahead and make an exponential out of it. Okay, I'm going to take 4 and raise the entire left side. If I do it to the left, I also must be able to do it to the right. This right here, the 4 to the log base 4 is going to cancel out. So now I have 5x minus 1 equals 4 cubed. And we know that 4 cubed should be 64. Add 1 to the other side, so I have 5x equals 65. And when I take 65 and I divide it by 5, I think I get x equals 13. We'll practice this more tomorrow in class together before we split off and start doing our homework. I hope you have a great night. I'll see you tomorrow.